we'll record. I hope you guys can hear me. I messed with the audio settings a little bit, but I think it's working. You guys responded when I talked to you. So, okay, it is week 7 Friday. I'm gonna get together with my readers and graders. I mean, virtually online via Zoom and stuff to grade your second midterm exams. We'll probably do that on Tuesday. I know, and I know I've been like super behind on posting grades, and I sincerely apologize. I feel like I'm barely holding it together with just getting your lectures together. So anyway, I will get your grades posted. So we will we'll do that, and yeah, homework grades we'll start to get those posted as well. I am sincerely apologize for the great delay in getting your stuff graded, but it will happen. I'll make sure you guys know where you stand. Anyway, we left off on Monday talking about support vector machines, and so today we'll kind of wrap up the talk on support vector machines. And okay. So we'll continue talking about support vector machines. And okay, so this is where we started. We started off talking about the maximum margin classifier, and we said, okay, we've got some data in 2-dimensional space, and what we want to do is we want to draw a linear hyperplane, which in 2D space is just a line. Okay, so we're going to draw a linear hyperplane or a line that's going to separate the positive from the minus points, the plus points from the minus points. And we're going to choose the hyperplane that maximizes the distance between kind of the nearest points to the plane. So here's the 2 nearest, or these are the 3 nearest points to the plane. Okay, as far as kind of perpendicular distance to the plane, you know, these two are equal, and these points are equally distant from the boundary here. And what we want to do is we want to maximize, we want the hyperplane that will have the widest margin, right? So we, this on Mondays I showed like possible hyperplanes, and the other ones did not have the widest margin. This one's going to have the widest margin, right? And so this becomes a matter of finding the definition, the vector that defines the hyperplane, and we want the one that's going to maximize the margin. And so the hyperplane is going to be the boundary, and that's going to be the set of x points. Okay, so basically the set of these points, which is all the ones that form this line, or in a higher dimensional space, all the ones that form some kind of plane that satisfy this equation, that W dotted, or you know, W transpose X is equal to some constant, or W transpose X minus B, or W transpose X plus B, depending on what you're looking at, is equals to 0, right? So we want to find the quantity, this quantity, okay, find the W that does this. We want the W that maximizes the width of the margin, okay? And so the way we're going to find that is we're going to take the vector x1 minus x2, that's the vector that joins the 2 closest points from either side, and we're going to take that, the dot product of that, with the direction perpendicular to the margin, which is W itself. So the vector that joins x1 and x2, which is kind of the vector that joins these 2 points, if we project that onto this perpendicular direction, okay, we're going to get this thing. Okay, so the perpendicular direction to the hyperplane is, you know, W over the norm of W, and we're going to dot that with the vector x1 minus x2. That will give us basically that purple arrow there, and the length of that purple arrow. And the length of that purple arrow, we're going to say is 2 gamma. And then I showed on Monday's lecture, we did some math, And we can say that after you simplify everything, this gamma is equal to 1 over the norm of W. And so what we want to do is we want to maximize this quantity. We want to maximize the gamma, and that can happen if we minimize this norm of W, right? So norm of W is in the denominator. Maximizing that distance gamma is equivalent to minimizing the norm W, okay? But there's the constraint that the W we choose correctly classifies all of our points, right? And so the current class label is T sub n, and this is either +1 or -1, a positive or negative value. And then what we're gonna do is we wanna multiply that by basically the value of x dotted with W minus some constant. And so this is gonna either be greater than 1 or whatever, or if it's on the negative side, this will be -1, but then T sub n itself will be negative, so it will also end up being greater than 1, okay? And so this relationship has to be true, this constraint has to be true for all of the, I should say for all n, for all of the values in our data set, okay? So optimization subject to constraints can be done with Lagrange multipliers. And when we use the Lagrange multiplier, we rewrite our objective function, okay? So the norm of W squared can be expressed as W transpose W, okay? And what we want to do is we want to minimize this thing, the norm of W, okay? But it's subject to all of these constraints. And so, so we're going to take each of these things, subtract the 1 from each side, and we get this, and then we multiply it by some constant alpha sub n, and alpha sub n has to be greater than 0, and this is the objective function that we want to optimize here, right? And on Monday I said there's no closed form solution, all right? And that's true, there's no closed form solution. But what we can do is we can kind of work with this a little bit. Simplify is probably not the right word, but what we can do is we can kind of re-express this in a few ways, and there's a few things we can learn after re-expressing this objective function. So here's the function that we want to minimize, right? Here's the function we want to optimize here, and what we can say is that at the minimum, the derivative of this function with respect to W and B, those derivatives are going to equal 0. So if I take the derivative of this with respect to W, or W transpose W, derivative of that is 2W, that 2 cancels out with the 1/2, and I get a W here. Okay, and then if I distribute the sum of alpha n Tn to the two terms inside of here, and also this term, okay, well, with respect to W, this is a constant, and this is a constant, so these go away to 0. And basically, I have alpha n Tn W transpose Xn. If I take the derivative of that with respect to W, I'm going to get the summation of alpha n Tn Xn. Okay, so if I say at the minimum, this derivative is equal to 0, then this relationship will also be true, that W is going to equal the sum of alpha n Tn Xn. Okay, that's what we're going to have at the optimum. And then if I do something similar and I take the derivative of this thing with respect to B, okay, this whole thing has no B, it's a constant, so it goes away to 0. And if I distribute all of these terms, the 1 goes away, this stuff goes away, and basically I have alpha n Tn times B. The derivative of that with respect to B is alpha n Tn, okay? And so we're going to say that is equal to 0, and there's a negative sign, but it's 0, so it doesn't matter. So we're going to get the sum of alpha n Tn has to equal 0, and we also say W is going to be the summation of alpha n Tn and Xn. All right, so on the next slide, it's going to look like a huge mess, and it is. But what I'm going to do is, again, we're going to say this is the function we want to optimize. This is the function we want to optimize, and I'm going to plug in we said at the minimum, this relationship is going to be true. W can be expressed as a summation of alpha n, t, and xn. I'm going to plug in this thing in everywhere I see W. Okay, so I'm going to replace this W with this. I'm going to replace this W with this, and I'm going to replace this W with this. Okay, so be prepared. The next slide is going to look a little crazy, but there we go. Okay, so I started off with that, 1/2 W transpose W, all of this, and for every W, I replace it with that summation A n, T, and Xn. Okay, so I got this, this, and this. All right. I've got a product of these things, and so to handle the different summations, I'm using different subscripts. So we're having the subscripts of m from 1 through n, and the subscript n from 1 through n. And I don't know, I'm probably made a typo mistake somewhere with all of these subscripts, but it should say alpha m, tm, xm, alpha n, tn, xn, double sum alpha n, tn, am, tm, xm, x, wait, yeah, yes, I think. All right, well, anyway, I think that's right. Okay, so anyway, you can, when you distribute these alpha n's and t n's with the m's and the t's and the x and the m, I think it looks like this, right? Okay, so anyway, all this to say, you can rearrange these terms. These two things are the same thing, or they not the same thing, they combine. So I've got a 1/2 of this minus a full one of these, so I get, and then this thing, sum of alpha n tn times b, well, we said the sum of alpha n tn equals 0. So this becomes 0. And I rearrange terms and I get the sum of alpha n minus, because this is a -1 and this is a plus 1/2, and we get minus 1/2 of this. Oh boy, all right. So anyway, this becomes the function that we want to optimize. All right, so that's the function we want to optimize. Did this really help? I don't know. Anyway, apparently this function can be solved. You can find the optimum of that using quadratic programming. And again, I say I don't know anything about quadratic programming, but apparently the computer can handle it. It's some kind of iterative method, and it's going to find the solution here via quadratic programming. And this, but what's interesting is that this function, the optimization problem, doesn't include W itself. So we don't need to worry about, we just need to find basically the alphas that will optimize this, okay? What value of alpha will optimize this, because X is a fixed value and T's are fixed values. These are directly from our data. And so really we're just messing around with the alphas. All the alphas have to be positive, and when you do the summation of the alphas times the class labels, they have to add up to 0. So it's a matter of finding these alphas, and that's what it is. Okay. If we take a look at kind of this this thing that we found earlier, we say, well, at the minimum, when we optimize it, the vector W, right? So the vector W is the vector that defines our hyperplane, okay? The vector W is equal to the summation of alpha n, tn, and xn, right? So let's take a look at that, right? So tn and xn, these are basically the location and the labels of our data points, okay? And we're basically saying W is equal to the sum of basically our vectors multiplied either by a plus or minus sign, okay? We're going to take the vectors of our data points multiplied by some constant alpha, and let's think about what this means. Okay, let me go back. So here's kind of the picture of the boundary that we want, right? So we want this boundary. The boundary is defined by our vector w, which is kind of the vector that represents the perpendicular direction or the normal direction to the boundary. And that vector w is defined, okay? Our boundary is defined just by our support vectors. The support vectors are basically the points in our data set that influence where the boundary exists. Now, these points, we said these points have no influence on this boundary. I could move these around, I can move these dots around, and these is, as long as these 3 points remain the 3 closest points to the boundary, the location of the boundary is not going to change, right? So these other points, these points down here in our data set, I can move them up here, put them over here, move them about. The location of our boundary is not affected, okay? The location of our boundary is solely influenced by these 3 points. Okay, so what does that mean? That means that when we find this vector w that defines our boundary, that means the alpha values are going to be 0 for anything that's not a support vector. If it's not one of the 3 points that define the location of the boundary, those alpha values are going to be 0. And then for the points that do define the boundary, those points will have non-zero alpha values, okay? So, so at the solution, the support vectors will have alpha values that are not 0. And then the other points, the non-support vectors, will have alpha equal to 0, right? The non-support vectors have no influence on the value of w, right? And so you can think of alpha as a measure of how much influence a particular value in the training data has on defining w, okay? So identifying w is a matter of finding the correct values of alpha, and apparently that can be done via quadratic programming, okay? Also on Monday, I talked about this idea of soft margins, okay? And the maximum margin classifier uses what we call a hard margin, in that when we do it, we say all the points have to be correctly classified. We're going to pick the boundary that's going to correctly classify all of the points. We're not going to allow any points to come into the margin or be classified wrong, okay? You can create something called a soft margin that says, you know what, let's get a boundary, and it's okay if some of the points end up inside of the margin. It's even okay if some of the points end up on the wrong side of the margin, okay? So rather than saying all the distances, basically the distance from the point, so this is kind of the distance from the point to the boundary, rather than saying they all have to be greater than 1, we're going to say, you know, we can allow points inside this margin, right? So if we say here's the boundary and the perpendicular distance from this point to this point, if we say if this is equal to 1, all of the points have to have a distance of 1 or more, and all of these points have to have a distance of 1 or more, because this distance is 1. We can say, you know what, it's okay to have a point inside the boundary where the distance is less than 1. It's even okay if a point is on the wrong side of the boundary, like having a plus point over here where the distance is actually going to be negative. So that's what having a soft margin is. And I'm skipping the math. You can check the textbook. But apparently, when you do a soft margin, the optimization problem, this part equals the same, except the constraints that we would use would be that the alpha value, which is basically how much influence a point can have, there's an upper limit to it, okay? A single point can't overly influence the boundary in such that it forces the boundary to conform to its will or something. That's the effect that it has on defining the boundary. Okay. All right, and another thing we can do is we can use kernel functions, okay? And so a kernel function allows us to find nonlinear boundaries, okay, by optimizing a very similar function, right? So this is the function that we're trying to optimize. We're trying to find the alpha values that optimize this function, like what values of alpha will optimize this. Well, we just change it. All we do is we change, so here we have basically the dot product of these two vectors, xm and xn. So we kind of look at every combination of 2 points, m and n, in our data set, and we say, all right, well, what if we replace this dot product with a kernel function, okay? And then we optimize that. Okay, so well, what's a kernel function, okay? A kernel function itself is an inner product, okay? Much like the dot product, okay? Itself is an inner product, but it's an inner product after we apply some transformation function. So you have a transformation function phi that transforms the data. So we've got our vectors in 2D space. We transform our data from 2D space into a higher dimensional space. We like project the data into higher dimensions, and then we take the inner product there. Okay. So I think this will make more sense if we apply if we do an example here. Okay. So here I've got here's my transformation function phi. Phi is going to project from x1, x2. Okay, we're going to we have a vector in 2D, and we're going to project it into 3D. Okay, so it's kind of like, well, I don't know. 3D movies used to be, I don't know, there was a few years where like 3D movies was a thing, and they would actually go back and they would take 2D movies and then they would like rework them to look 3D, right? So this is like, I don't know, they had like Titanic got re-released in 3D. I don't know if anyone's even seen the movie Titanic, but they took these movies that were originally shot in 2D, and then they like did stuff to them and basically turned them into 3D movies. And we're doing something similar. Our data exists in 2 dimensions, and here I'm using this phi function that projects it into 3D, okay? If you haven't seen Titanic, you should watch it. It's a great movie. It takes 3 hours long, but it's enjoyable. But we're taking this 2D vector and we transform it into 3D. And so basically, all I'm doing is I'm leaving x1 and x2 untouched, but I'm adding a third component, which is going to be x1 squared plus x2 squared. So I'm saying here's a third dimension. So we take our 2D and we project it into 3D. Okay. So then, so let me just show you what happens when you do this to a to 2 vectors here, right? So let's say I've got vector xn and vector xm. Xn is the vector 1, 1. Xm is the vector 5, 1. And if I apply this onto xn, okay, I'm going to get x1, which is 1, x2, which is 1, and then I have x1 squared, which is 1 squared, x2 squared, which is 1 squared, so I'm going to get the vector 1, 1, 2. And then xm is 5, 1, okay, x1 is 5, x2 is 1, and then x1 squared is 5 squared, and x1 squared is 1 squared. So when you do that, you get 5, 1, and 26, okay? And so the kernel function is going to be basically the dot product or the inner product of these 2 vectors after we've transformed them. So we take our 2D function, our 2D vector, we transform them into 3D, okay? And so now I get the vectors 1, 1, 2 and 5, 1, 26. And we take the dot product of these and we get 1 times 5 plus 1 times 1 plus 2 times 26. So 1 times 5 is 5 plus 1 plus 2 times 26 is 52. So 5 plus 1 plus 52 is equal to 58, okay? So, so rather than just doing the inner product or the dot product of these 2D functions, which are 2D vectors, I'm getting the inner product of basically these three-dimensional vectors. Okay, and I get this number 58. So here's the thing. You don't actually need to know what this transformation function phi is, okay? Like this was an illustration, and we can see how it worked, okay? But you don't actually need to know the transformation function phi, okay? If our transformation function phi is this, the kernel function can also just be expressed as this. So we can say, you know, the kernel function is the inner product or the dot product of these vectors after we've transformed them, but the kernel function can also just be expressed as an expression of the original vectors themselves. So here I can just do xm, the dot product of xm xn plus the norm of xm squared times the norm of xn squared, okay? So I don't even need to transform xm and xn into 3D. I can just deal with xm and xn directly. So let me just kind of illustrate that. So here xm and xn are these two 2D vectors, okay? And on the previous slide, or the 2 slides ago, we said we can transform them into 3D, take the dot product of those things, and we get 58, okay? But here I can just use them directly on the input vectors, right? So here's the kernel function. The equivalent kernel function can just be xm transpose xn, okay, which is basically the inner product of 1, 1 and 5, 1, plus xm norm squared and xn norm squared, okay? So the inner product of 1, 1, 5, 1 is going to be 1 times 5 plus 1 times 1. And then xm, the norm of xm squared is going to be 1 squared plus 1 squared. And the norm of, I might have gotten these m's and n labels mixed up. And the norm of this thing is going to be 5 squared plus 1 squared. And so, so this becomes 2, and this becomes 26. And now I have 1 times 5 plus 1 times 1 plus 2 times 26. And I also get 58. So I get the same value, 58 and 58, whether I transform them into 3D and then take the dot product, or if I just have this expression, which is the kernel function, I can get the equivalent result, okay? And so the point isn't that we have to figure out, okay, well, here's our transformation function and here's the equivalent kernel, okay? If you try to figure out what the equivalent transformation function is, you know, sometimes you're going to run into problems because the transformation function could actually be like an infinite dimension. The point isn't that, it's just that here we can replace the expression in our optimization problem to just be a kernel function, okay? And we're going to use kind of these values, okay? This value 58 or whatever it is to kind of figure out what alpha is that I need to use, okay? So why is this useful? Well, the reason this is useful is basically when you use a kernel function, it's equivalent to using that phi function to project it into the higher dimensional space, right? And so what you might have is that in 2-dimensional space, there's no linear boundary that separates your points, but you can transform it into a higher dimensional space. And in the higher dimensional space, maybe there is a linear boundary, a linear hyperplane that will split the data, all right? And so here we have an animation that shows this being done. Okay, we got to endure a commercial first. All right, thank you, Grammarly. Okay. So here, this is, the video is now 13 years old, but so basically, I don't know if you guys can see this, but on this plane, we've got dots inside here are blue, and dots outside the circle are red, okay? And so there's no linear boundary that exists in 2D that can separate the red points from the blue points, okay? In 2D, there's no linear boundary that can separate the red points from the blue points. So we use a kernel, okay, much like this one, okay, so we're going to use we can use the kernel function, but it's equivalent to transforming each point into 3 dimensions, okay? So we're going to project the data into 3D space. So this is what it looks like. Basically the x1 and x2 values, are untouched, but we're adding a 3rd dimension, okay? So here, let's look at that again. So the data gets a 3rd dimension added to it, okay? And so here's our data now projected in 3D. And now that it's projected in 3D, we can have a linear hyperplane. A linear hyperplane exists that separates our data, the blue from the red, okay? So in 3 dimensions, a hyperplane exists that can linear hyperplane exists that separates this, okay? And so with that, we can now see, well, what does that hyperplane separation look like in 2D? It looks like this, okay? So it looks kind of, looks like a circle, but it's a good animation here. So we take our 2D data, we project it into higher dimensions, in this case 3D, because we can visualize that. And in 3D, a linear hyperplane exists that separates the data, and now we can use basically the maximum margin classifier idea on this projected data, and this becomes the boundary that it finds. Okay, so that's known as kind of the kernel trick, or the kernel method there, is that we can find a linear hyperplane that separates our data, even though in 2D it doesn't work. Now, and so there are a bunch of different kernel functions, we call these kind of positive definite kernels, that exist that will transform your data from a lower dimensional space to a higher dimensional space. Now, what we visualized was going from 2D to 3D, because we can visualize both 2D space and visualize 3D space. But a lot of these kernels will actually transform to like a really high dimensionality. Like you can take a polynomial kernel and it can project it into like 12 dimensions or something, okay? Now, and we can't visualize 12-dimensional space, like our brains just can't do that. And one of the most popular kernels is the radial basis function, or the Gaussian kernel. And that kernel actually transforms, your maybe like a point in 2D, it actually transforms it into infinite dimensional space, okay? Because it's based on the Taylor expansion of the exponential function. And so, your Taylor expansion is an infinitely long series, and it's based on that. And so it actually transforms your 2-dimensional vector into an infinite dimensional vector, and takes the inner product. But you don't actually have to. You don't actually have to transform it to infinite D and take the inner product. You can just use the kernel function directly, right? So that's kind of the thing, is that you don't actually have to. Like, it's nice for us to visualize and help our brains get our heads wrapped around it. You don't actually have to transform it into the higher dimensionality. You can just apply the kernel function directly on the vectors themselves. And so there's a radial basis function, which is a kernel function that applies directly to the functions themselves, and it would give you the equivalent result of transforming it into an infinite dimensional space and taking the inner product. But again, you don't actually have to do that. So you just apply the kernel function directly and onto the vectors, and it will work there. Is that right? Okay. So this is basically your homework problem, and I've created a bunch of graphs here. And so in your homework, I said, I want you to kind of mess around with SVM and try to understand some of these parameters that can be used. And so the Gaussian kernel, or the radial basis function, same thing, comes with a couple parameters that you can mess around with. And okay, so anyway, this is the data that we want to try to draw a classifier boundary for. This data comes from a package, Elements of Statistical Learning. And I'm sorry, apparently this package has been archived. I guess nobody has updated it in a while, and so it has been archived. So you can't actually install it the traditional way. You're gonna have to use the dev tools. So you gotta install dev tools, and then the package is available on GitHub, and you can install it from GitHub. So, so I'm sorry about that. But that's what, but you can get the data from there. So, so anyway, we want to draw some kind of boundary that separates this. And obviously we can't draw a linear boundary. That's going to be 100% successful, but we can try. And so, so SVM will show us kind of potential candidate locations here. And so, so there's a package E1071, and you can just say, hey, let's make a support vector machine use a linear boundary here, linear kernel. And there you go. This is the best linear boundary that we can get that separates kind of the black from the red. You know, some misclassifications, but we go, okay, well, I guess that's all right. All right, there's other ones you can use, right? You can use a polynomial kernel, all right? And so here's a third degree polynomial kernel. There's also different parameters you can mess around with. And this ends up being the boundary that a degree 3 polynomial creates. And so this is, the dark line is the boundary. And so again, what this is doing is it's projecting the data into some higher dimensional space. I don't know exactly what dimensionality is. And in this higher dimensional space, we are drawing some linear hyperplane that cuts through the data. And when you project it back down to 2D, this is the representation. These lines here are basically parallel lines in the higher dimensional space. Again, we can't visualize this high dimensional space because I think our brains can only really visualize 2D and 3D, maybe 4D, but not really. So this, so we can't really visualize it, but this would be the equivalent of drawing some linear hyperplane in the high dimensional space. Okay, you can mess around with higher degree polynomials and you'll get weird shapes. I don't know if this is any better. It doesn't seem better, but this is just kind of what it ends up producing. Okay, probably the most popular kernel function though is the Gaussian kernel, or the radial basis function. And because it offers quite a bit of flexibility, right? And there's a few things. There's the gamma and cost parameters that you can mess around with for this, all right? And so this is basically your homework assignment. So I'm not going to give you all of the answers here, but what I've done is in these lecture slides, I've produced a lot more plots. I think in your homework, I produced maybe like 6 plots or 4 plots. I don't remember. But here I've produced like, I don't know, 20 something of these things. And maybe it'll give you a better sense of what changing gamma and cost will do, okay? So this is the plot we get, kind of the default settings. Gamma is 0.5 and cost is 1. And this is the boundary that it draws, and these are kind of parallel hyperplanes. So again, this projects the data into infinite dimensional space, which we cannot comprehend, but each of these points gets projected into this very hot infinite dimensional space, and once it's projected in that space, we're drawing some kind of linear hyperplane, and this is the representation of that hyperplane that gets drawn. We go, okay, well, seems to do a decent job of classifying black and red with the default settings. So let me just show you what happens. when you alter gamma. So here I'm going to keep cost at 1. Keep cost at 1, and I'm going to start off with gamma equal to 0.1. So here's gamma 0.1, so low gamma, and you get this smooth line. And then gamma 0.3, gamma 0.5, gamma 1, gamma 2, gamma 5, gamma 10. So let's just, this is what can happen. Okay. What did I do? I messed something up here. Okay. I'll fix that. All right. So that's what happens when you mess with gamma. So gamma small to gamma high. Okay. And I want you to comment on what happens when you alter gamma. All right, and then so here we're going to keep gamma at 0.1. I'm sorry, 0.5. Keep gamma at 0.5, and let me just show you what happens when you alter the cost. So here's cost 0.1, cost 0.5, cost 1, cost 2, cost 5, cost 10. Okay. So what happens when you increase the cost here? All right, and that's gamma with 0.5. Here's gamma equal to 2, cost is 0.1. And as I increase the cost, that's what we get, okay? So here's gamma 2, cost is 0.1, and I'm increasing the cost up to 10, keeping gamma equal to 2. And then here I'll do this, I think one more time. Gamma is now 5, and I'm gonna keep the cost at 0.1 and push the cost up. Okay, so what happens when you alter the cost? Okay, this is altering the cost at different levels of gamma, and then what happens when you alter the gamma itself? So those are things I want you to kind of study and look at, and you can look at these slides, and you can look at kind of the plots that we've produced in your homework assignment. And that's just with the radial basis function, the Gaussian kernel, which is probably the most flexible and probably most frequently used kernel functions for support vector machines. And again, the idea is it projects it into some high dimensional space, and in high dimensional space, it is finding some linear hyperplane. And yeah, it's and it's equivalent to applying some kind of transformation function that works. But again, we don't actually have to transform the functions. We can just apply the kernel function directly to the vectors themselves. Okay, that's all I've got for you guys today. So we'll wrap it up there. Give us some time to get your midterms graded, and we'll get those posted. And other than that, have a good weekend. And oh wait, I have to give you your quiz answers. The quiz answers, yeah, thank you. A 7th week Friday. Okay, your quiz answers are A and B. Apple and banana, A and B. Apple for the first, banana for the second, alpha, beta, I don't know, alpha, bravo, AB for your quiz today. Okay, that's it. Have a good weekend, you guys, and we'll see you Monday.